Hi, and welcome back to the second part of Elette Boyle's session on function secret sharing.
All right, thanks, guys. So actually, just to answer a quick question, one of the questions that came up during the break was about, for the additive reconstruction, does it truly need to be just additive? Or could something like Shamir secret shares work? And the answer is indeed. Actually, it just needs that the reconstruction is some linear function of the output shares. So for example, Shamir secret sharing has a linear reconstruction of interpolation. So it does extend a bit beyond additive, but I'm keeping it simple and just saying additive for today. Okay, so proceeding forward with part two. Now that I've got you guys all into this function secret sharing notion, maybe, I want to show you how can you actually construct this. And as I mentioned, so there were all these different levels of complexity and richness of function classes that we can get for function secret sharing, or its related notion, homomorphic secret sharing. And I'm going to give two examples on a relatively low level, because these are two of actually maybe the most useful and lightweight and very efficient constructions that are out there. So these are going to be for two different function classes. The first is the class of point functions, and the second will be a slight generalization of comparison functions. Okay, so let me begin with point functions. And again, so I'm going to use the terminology of FSS for point functions and distributed point functions interchangeably. These really just mean the same thing. And let me start by giving just a little bit of a history. So the first constructions of DPFs from one-way functions actually go back before all of this function secret sharing time. There's an implicit construction in Scholl-Gilboa, where they were doing two-server private information retrieval from computational assumptions. And if you actually go and open the box there, what you get is something that does satisfy the properties of a DPF, but with relatively large share size. Okay, so explaining what I'm writing here, the numbers are going to be the size of one of the function shares. And remember that I'm maintaining that n is the number of bits of input for the function, and lambda is the security parameter. Okay, so the first time actually the term distributed point function was coined, this was a work of Gilboa and Ishai before my time, slightly before I entered the scene in 2014. They showed a really cool recursive version of this, where very, very loosely you can describe a point function as sort of a tensor of two smaller point functions. And then each of those, in fact, is a point function that can be expressed as a tensor of smaller point functions and so forth. Not going into details there. And the complexity that you end up getting here, so each time you cut the input bit length by half, but you instead of getting one big point function, you end up getting three in the process. So here, this n to the 1.58, this is the exponent is actually base 2 logarithm of 3. Okay, but it's strictly more than n to the 1. Okay, then starting in 2015, so this is when I joined in and became part of this. So this was the paper that is function secret sharing, ZeroCrypt 2015. And one of the things that we show in that paper is an improved DPF construction based on a tree structure that got rid of this n to the 1.58 and instead had a linear term of n in there. And in fact, also we're dropping the asymptotics that really is something like 4 times n times lambda. And roughly what that comes from there is that in each level of the tree here, so depth n, that there were 4 sort of lambda sized strings plus a little bit of extra that you needed to give as part of the function key. So out of interest, year or a couple years after this paper, we actually realized that you can view this as an abstraction, that it really is a form of the recursive structure, but with a very different recursion. So instead of half and half, that you end up doing like n-1 and 1. But so the best construction to date is an optimized version of this tree, which itself doesn't quite fit in the recursive framework. And then we got rid of basically this factor of 4. So this was in a CCS paper together with a couple other results as well. And loosely what that corresponds to is that for each level of the tree, you have something like lambda bits plus a bit of extra. And I'm putting here explicitly question marks. I would love to drop the size of this DPF construction. It's something we've worked on. It's something others have worked on. It's kind of at the point where I don't know how to shave anything off of this in any sort of interesting way. And this is a really motivated question, I think, because of sort of the piles of applications that would automatically get bumped up and improved given this. So I leave that as an open question for the viewers. Okay, so let's actually build this thing. Now I'll be describing the construction from BGI 16b. Okay, and the tools that we have at our hand is going to be a pseudorandom generator. So this is a cryptographic tool. It takes a seed of say, security parameter many bits and outputs something that looks random. It'll be much longer. And I'm going to consider something that's roughly length doubling. Actually, it's going to be a little bit more than that. Okay, and how to implement this efficiently. I told you there's all these efficient implementations of these things. So for example, you can roughly emulate this via 2 calls to AES, and there's a lot of interesting work about how to do that. Okay, another useful tool, which we're not going to use directly, but the structure will be very analogous to, is the Goldwasser-Micali pseudorandom function construction. So hopefully you guys have seen this. This is a way of converting a length doubling PRG to entire long pseudorandom string, where in every single level of the tree you can kind of go left or go right from the expansion of the next level, and then you take for example, the right and expand that as well. Okay, so at a very high level picture, what the construction is going to look like is as follows. Okay, so the first part of the key here, the left and the right, are representing the key that I'm going to be giving to party 1 and party 2. Sorry, party 0 and party 1. The first thing I'm going to give is just a random PRG seed, different each of them. Okay, so if you were to expand out this entire GGM tree, this would give you 2 completely independent pseudorandom looking trees. Okay, this is not what we want, but what we want, remember, is effectively secret sharing of something that's equal almost everywhere, but is different at exactly one special point, which corresponds to the special point function point alpha. Okay, and how this will be executed is by giving so-called correction words, the CWI at each level, that is somehow, and you'll see how it'll somehow force equality of the 2 sides as soon as you go along the path and you leave the path that disagrees with the special value. Okay, so for example, here, the special value goes to the right. So anything that goes off to the left, I want to somehow force the subtree below it and all of the ancestors there to agree with what is on the left-hand side. Okay, and the correction words are going to kind of enforce this subtree by subtree that are hanging off of the special path, leaving just one special alpha point where they're different. Okay, and now I want to really get more explicit about this. Okay, so suppose that I have a point function. This is my secret f alpha going from 0, 1 to the n to 0, 1. And these, I'm going to represent sort of these trees on the 2 sides of the keys. Okay, and the invariant that we're going to maintain in this construction for the evaluation, and by the way, I'm sort of going to talk about the gen and the eval a little bit smeared one into each other, but I'll explain a little bit afterward what's going on. Okay, but we're going to build the key such that when you do the evaluation, at every single node along your evaluation path, okay, so suppose, for example, I want to evaluate on some different input, and maybe this input down here, that as we're evaluating at every node in this tree, each of us is going to compute some value, in just a second, okay, which is going to have 2 parts to it. One part is the length of the security parameter, okay, that I'm going to represent that by this kind of rectangle chunk, and the other part will be a single bit. Okay, and the invariant that we'll have, so for every single node, I'll have some string and some bit, some string and some bit, and we're going to build this in such a way that for every node on the special evaluation path, here, I mean, this is the path down to the special point alpha, the values that we have, the square and the bit, will correspond to an additive secret sharing of some S and some B, okay? Such that when we're on the special path, these are secret shares of some random or pseudo-random value. What do I mean by that? I mean that this is some string that is totally pseudo-random and independent from the other string. In particular, if I know my string, I don't know anything about yours computationally. And the bit, when we're on the path, the bit will be a secret share of 1. That means whatever specific bit I see right here is the opposite of the bit that you see here. Okay, this is the invariant for the values along the path. Okay, for example, here and here, these will be pseudo-random and different, and these will be different bits. On the other hand, as soon as you go off this special path, okay, so for example, if I'm going to the left here, whereas the special path goes to the right, then my secret shared values will be 0 and 0. And what that means is whatever I have over here, you have the identical strings over here. Okay, so all of my values here, my secret sharing and so forth are going to be over sort of XOR arithmetic. Okay, so I can certainly start this out. This is easy to do for the root, right? I just give you this seed and this bit, and I give you this other seed and this bit. And the question is, how can we somehow build the construction so that these invariants will be maintained? Okay, so let's kind of use our magnifying glass here and zoom in. And sort of the tricky part is, as soon as we go off the path, as I mentioned before, we need to somehow now force that you're going to agree. Whereas up at this node, we have different values. And if you go to the left, I want to somehow force what you're getting over here to agree with each other. Okay, we do that by what we refer to as sort of a conditional correction gadget. Okay, and now even kind of take a step back, and I want to think slightly more abstractly. Suppose that we hold on to secret shares of some value R. Okay, this can even be longer, this could be short, whatever. Okay, this is some length K string where K is some value. Okay, so explicitly, my blue circle here is, it's not a circle, my blue rectangle here is a value R0. Okay, and whatever you have is equal to my R0 XOR this value R. So this middle line here is my notation of what you get if you add the two pieces together. That is, our pieces are secret share of R in this case. Okay, and similar for B. And suppose now that there's some public value that we both see, which I'm calling delta. Okay, the conditional correction operation is going to take these two things and output a new share value, okay, which is forms, oops, okay, don't mind the zeros going to ones and the ones going to twos. This is I'll fix the slides afterward, okay? This is supposed to represent taking this R0 plus delta, okay, delta is the same length, it lines up with my R0, but I take delta times B1, okay? What does that mean? That means if my B0, sorry, if my bit here is 0, I don't add in delta. But if my bit is 1, then I do add in delta. That's what this represents. Okay, so I do this operation and you do the same operation. What does that give us shares of? Okay, well, the R1 and the R2 are already shares of capital R. And the fact that I've got B1 times delta plus, now if I put our shares together, B2 times delta, this gives me exactly plus B times delta. Okay, because remember the B is B0 plus B1. Okay, so I claim, maybe this is not obvious yet, that we've just made fantastic progress. And let's see, let me give you a little bit of a flavor of this. Okay, so test yourself. What happens if, for example, R is the all zero string, okay, that is whatever I'm holding on to is the same as what you're holding on to, and B is also 0. What shares have we just generated? We've generated shares of, somewhere around 200 people, and I don't see any of you. So I'm going to answer the question myself. What?
I said I can take over for the people, I guess. It's 0.
Excellent. It's 0. Hooray. Good. Okay. So what is this saying? This is saying if I started such that we already agreed on our strings and our B, what I'm getting is going to be the same on both sides. That shouldn't be a surprise, actually, because we're both doing exactly the same operation. Okay, that is, we're maintaining secret shares of 0. Now, slightly interesting. Okay, so suppose that B is equal to 1 and delta is equal to R. What do we get? Shares of, okay, so I have R plus 1 times delta. This is going to be R plus delta. But if delta is equal to R, I'm again getting secret shares of 0. Okay, and this is the interesting progress. So what is this saying? This is saying, suppose that I have different R values. Okay, my R0 is different from your R1. We're secret sharing some string R. Okay, but if our bits disagree, and if I can set this delta, for example, to be equal to what our values are secret sharing, note that that's not equal to either of our values, but it's the sum of our two values, then we've just converted our secret shares of R and 1 to secret shares of 0. And this combination is going to be what allows us to sort of zero out as soon as we go off the path. Okay, so let's be more explicit here. In fact, what is this delta, this magical delta that I want to set to? Okay, so this slide was a bit abstract. There's some capital R. How does that actually correspond to our construction? Okay, so remember that we're interested in this magnifying glass here, where we're at some node that's on the path. It's a blue node. Okay, what does that mean? That means that each of you and I have some string and some bits, okay, that corresponds to that node, where the strings are different pseudorandom and the bits are opposite bits. And what we're trying to get to is such that if you continue to the left, I want to get a string and a bit that'll now be identical across the two of ours, because this is when we're going off the path. Whereas if you continue to the right, I want to maintain that what you're holding on to is some sort of secret sharing of a pseudorandom and 1. Okay, so let me write this out more explicitly. So we're starting, indeed, I'm maintaining this central position as what I'm the secret shared value. I feel like I should also mention I've inherited this fluorescent red from some other prior version of the slides. It's amazing how we've kind of bounced back and forth with different co-authors, and we've built up the construction slides for this construction since 2015, really. Okay, so this is what we're starting with, secret shares of S and 1. The first thing that will happen in the construction, so each person is taking their seed and expanding their seed out with a pseudorandom generator. Okay, this is now going to be playing the role of this R0 and R1, like in our previous slide. Okay, and what are these secret shares of? Well, I started with basically random independent values. I'm using a pseudorandom generator. What I'm getting is also just going to be R0 and R1 are pseudo-random independent values. Okay, so what they're secret sharing is just some sort of random looking garbage. Okay. But I want to take this garbage. We're going to use this, swim around in the garbage, and consider taking the string and parsing it into pieces. Okay, so indeed, I just have, these are two long pseudorandom values, but let's think about this as a string and a bit on the left and a string and a bit on the right. Okay, recall that the pseudorandom generator is roughly length doubling. It's actually going to be 2 seeds plus 2 extra bits. It's a little bit more than length doubling. Okay, so this is what we have, and this SLBL, this is just what I'm naming, whatever this region is of this induced value, this bright red string here. Okay, so this is what we have. And the goal is to build some delta. This is what we're doing on this slide, where the goal, okay, of once we use this conditional correction gadget, the goal will be that I want to continue on the left with zeroed out. As I said, as soon as we go off the path, I want to force it so that the string and bit that I get on the left agrees with that. This guy's string and bit will correspond to the string and bit on the other side. Equivalently, I have secretures of 0 in these positions. Okay. Whereas when you continue along the path, I want to maintain the second invariant, that as I'm along the path, I keep this pseudo-random some S prime, okay, and secretures of 1, so that our bits continue to disagree along the path. Okay, so this setup is probably even more complex than what's about to happen. And now the question is, what is the delta that I should put in here, such that when you take this string and you add in delta, you get the goal string? And indeed, if you take a look, for example, here I need to zero out SL, so I'll put a copy of SL. Same for BL. Here I want this to go to a secret of 1. So what I'm going to put here is the opposite. Basically, this is whatever the BR is plus 1. This is the negation of BR. And here, so technically, if I'm trying to get to some string S prime, what I should put here is SR plus S prime, and this will cancel out the SR and give you S prime. Okay, so let me say that actually, this works. This construction. I mean, I haven't shown you the full construction yet. This will yield a solution, but there's actually a point of optimization here, where you don't actually need a fresh new S prime each time, but actually you can reuse a piece of this delta. If I use the same SL on both sides, I'm choosing the SL. I need this to be exactly SL over here to cancel this out and get us to 0. And here I have SR. Now I'm adding SL, okay? But the point is that SL and SR were sort of pseudo-random with respect to each other in any case. So if I add these together, it also is something that's going to look pseudo-random. Okay, so this is one of the optimizations, in fact, that drops the key size down by this factor of 4. This gives you a factor of 2. Okay, so loosely, this is going to be this delta. And now let me be more explicit about how does this work in the construction. Okay, so suppose that we've gone and we've computed partway down the tree, and we've reached some point where indeed we're at one of these, where if I go to the left, it's going to go off the path, and if I go to the right, I maintain on the path. Okay, and say for concreteness, I know that these strings are different than pseudo-random, and say for concreteness, you have a 0 and I have a 1. In any case, it's either 0, 1 or 1, 0, because I know that these are secreture of 1. Okay, as we said, what you do, you take your seed and you expand it out with the PRG, and you parse it into these 4 different parts. Now, if you have a 1, okay, if your bit is 1, remember, this is your B, your share of the bit B. If you have a 1, then you add in the correction word, okay, which is going to have this particular structure from the previous slide, but this is some correction word. This is part of your key. Say, okay, this is the correction word for this level. I'm going to add it in. And if you have a 0, you don't add it in. Okay, so if you have a 0 here, then what you're continuing to the next level, so I'm taking this string and a bit, which correspond to this node, and I'm building a string and a bit for the 2 children. This will be the left child's, and this will be the right child's for this party. Okay, and this guy over here is going to take his extended string that's been parsed, add in the correction word, and kind of filling in how we actually built the correction word. Okay, this is if you sit and kind of think about it, this is exactly the sum of this. This is exactly what the value is that was secret shared across the 2 of us, for example. Then this is constructed so that when I add this in, this cancels out and I get exactly to what you were holding on to over here. But over here, the R's and the L's are giving me some sort of random looking thing. Okay, this is not canceling out. And over here, this is built to exactly leave you with the opposite of what's the string over here, the bit over here. Okay, so when you're on the path, the important part is that your bits are opposite. So when you're on the path, exactly one of the two parties actually adds in this correction word, which allows you to kind of program in what the change is going to be as soon as you go off the path. Suppose that I'm already off the path, okay? Then why am I going to maintain this invariant as well? Well, if I'm off the path here, so none of this is the highlighted blue, then what that means is the strings that we have are the same. The strings are the same and the bits are the same. Okay, so for example, suppose that the bits are both 0. Then when I expand, I still get the same. And the fact that they're both 0 means neither of us adds in the correction word, which means we maintain the same. Okay, the other option, if I'm off the path, is that we both have the bit 1. Okay, still I have the same seed. I'm expanding out to the same. And since we both have the bit 1, both of us add the correction word in. Okay, but now, since we're both adding it in, we get to some new green thing, but this green thing is identical across the two sides. Okay, so this is exactly maintaining the invariant that we require. Okay, so putting kind of the pieces together, what does the key end up looking like? Okay, well, remember that in each level, I needed some correction word, and this correction word had these 4 parts. Okay, but it was chosen so that this second part is identical to the first part of the seeds. This was the optimization that I mentioned, where you don't need this fresh random injection S prime, which means that I can describe this correction word for this level with exactly 1 seed and 2 bits. Okay, so putting all the levels together, at the top level, you have 1 seed, okay, that I'm giving. This is like the starting point where the 2 parties get 2 different seeds. Note, by the way, I'm not explicitly giving you a bit because you honestly don't need it. I know that at the root, no matter what your alpha is, the root is always on the path, which means we always have a secret sharing of 1. Okay, in which case you can just canonically decide, okay, I'll be the 0 person and you'll be the 1 person. There's no need to actually give you secret shares of 1. There's nothing you're hiding anyway. Okay, so this is at the root. And for each level along the tree, we have exactly one of these correction words, which has the form of some lambda bit string plus 2 bits. Okay, and all in all, so this is exactly the structure of the key. Each one of the keys is lambda for the top layer plus lambda plus 2 times n bits. And this is the key length of the construction. Okay, let me pause and see if there are any questions here.
Actually, there are no questions so far. Since
okay, excellent. Either you guys are dead, or my colorful rectangles did something.
That just appeared one question while I was telling you that there's none, and this is why isn't it 2 lambda at the start but only 1 lambda?
Okay, good. So this is this optimization that I mentioned. In fact, the original construction had like 4 copies of these string plus bit for each correction word, and we're able to cut down 2 of those factors of 2. And the second one here is indeed, so why don't I need 2 lambda? And the reason is because even though this string is of length 2 times lambda plus 1, which will give you 2 lambda plus 2, we've kind of craftily made it so that the second part here is identical to the first part. So here, maybe I'll go back over here. So I'm the thing that we're adding in, or what is this sort of lambda bit strings worth that goes in the correction word, is exactly the value that's going to zero out the difference between my lambda bit string here and your lambda bit string here. So it's exactly the sum of the 2. And so this suffices to give us to zero out our difference, or rather to kind of change your value into my value in this position. So we need that for sure. We need those bits in order to do this zeroing out. And the observation here, the optimization, is that I might as well use that over here. Really, basically, I don't need to actually take any action over here for this string, because we already have my red string and your blue string are pseudo-random and independent. This is kind of what we're maintaining. So I don't even actually need to do anything over here. And the observation is that, okay, well, by adding in the same string, which is your left plus my left thing, that it's not going to hurt the randomness, because it's independent, like pseudo-independent, that it's not going to kind of erase the random difference that's between us, and it will maintain that. So altogether, what does that mean? That means that I don't actually need to give you the second string a second time, because it's an identical copy of this string over here. So this is where we get to lambda plus 2 bits.
Okay, thanks. And at the top level, actually, you have, like, if you go to the next slide, or at the top level, you have like 2 seeds, but in your formula, you only have 1 seed. So why is it just 1 seed in your formula?
Okay. So this is this formula is just for one person's key. So if you're taking the 2 keys together, then it's all of that times 2. Yeah, I'm just trying to center it on one of the boxes.
Okay,
so whenever
thanks.
I talk about key size, that's the size of one of the keys.
Okay, thanks.
Okay, so kind of closing up this DPF construction. So we talked about the size of the key. These are coming from the correction words. A little bit about the computation costs. So in order to generate this key, what are the processes that you need to do? Well, very loosely, you kind of need to follow along on this path and figure out what are the actual PRG evaluations and computations that you're going to get in order to figure out what are the correction words that I need in order to zero these differences out. Okay, so the generation is going to be roughly n PRG evaluations plus some XORs. And this is also the cost of one evaluation. So if I'm evaluating at a single input, in order to go down the path at every layer, I need to do the PRG evaluation, possibly add something in, and then go left or right, then do another PRG evaluation and possibly add something in and go left or right. And just to give you one idea, going back to this application of private information retrieval. So for example, suppose that my database has 2 to the 25 records, each record is length D. Then plugging in this specific construction, for example, you can do this with, like roughly 2 kilobits, sorry, per server, like being sent to each server. This is the size of each key, and each server will send exactly D bits in return. The computation here, what's kind of cool is that actually the computation of the DPF, like this evaluation, is cheap enough that the computation cost is going to be dominated by even just the cost of reading these values and XORing the records. So this is kind of an exciting case where the cryptography itself is not the bottleneck. And even continuing a little bit further on this path, there's a couple optimizations that you can do for things like peer type applications. One of which is that if I have, say that my database has 2 to the n data items in it, I don't actually need to go all the way down to depth n, because the things that we're kind of computing along the way here, I've got these entire lambda bit strings that I'm maintaining, and roughly you can sort of pack in lambda different outputs into each one of these strings. So effectively what that means is instead of doing depth all the way down to n, I can trim off the final log lambda layers because I'm already getting kind of the number of bits here is already going to be big enough, because in each of these leaves, these intermediate leaves, I already have lambda bits. Another one, for example, so I mentioned that for private information retrieval type applications, you need to evaluate this FSS on every single input. Okay, and one way that you can do that, of course, is by evaluating on one and then starting fresh and evaluating on another and so forth. But obviously with this nice tree structure, we can leverage something a bit better, which is that I don't need to do log or rather kind of depth cost independently for each output, but rather I only need to evaluate each node of the tree once. So this gives you roughly a saving factor of 2. And as I mentioned, kind of putting these things on top of each other, the lookup cost and the XORs themselves end up becoming a dominating factor. Okay, a few final observations now, taking a higher look of things about the construction. One which is also relevant for this optimization that I mentioned is that there's an incremental sort of evaluation structure, which ends up being useful in a lot of different ways. And one thing that's a bit perhaps less obvious is that secretly inside this DPF construction, there's also a construction for an all prefix FSS. So what do I mean by that? I mean that if I give you this key that in effect was just trying to give you DPF for length n bit inputs for one specific alpha right here, you can actually already use this key to also evaluate bit outputs for any prefix match that you might want. Okay, so for example, suppose that I give you some input that's just a prefix. It's not a full n bit input, but say it's 5 bits. Okay, this key already allows you to generate a secret sharing of whether these 5 bits are indeed a prefix of the special input alpha. Okay, so I claim that in fact this FSS is hidden inside. If anyone can take a look and see where is it hidden in this picture, and this is the answer. Okay, so remember we maintained this invariant in the construction that at every single node, if you were on the path, in particular your bits are a secret sharing of 1. If you're off the path, your bits are a secret sharing of 0. So what that means is that if I evaluate, say on the first 5 bits and I stop, I don't actually do the full DPF evaluation, that gives me some string and some bit here. And that bit is already a secret sharing across our two computed values of whether this 5 bits is indeed a prefix of the special input alpha. Okay, so this is a relatively new observation. Another observation, which comes, I think, a bit surprising, it certainly was surprising to us when we first built this, is that almost everything in the 2 keys is identical and public, in fact. Okay, so there's, it's not a coincidence here that this green is the same color as this green. These correction words are the same, they're identical across the 2 parties. Remember, these are like the deltas for each of the level. And so one interesting thing here is that, the only thing that's actually different across our 2 shares is just these random independent seeds in the first level. So this is interesting on its own, of course, but something that we've observed more recently, and this I'm saying these 2 properties came up explicitly in this work joint with Dan and Henry, together with me and Niva, on private heavy hitters, that these properties actually can be leveraged and are useful for applications. So for example, without getting much further into it, the fact that when you're generating these keys, almost everything is the same across, and you can kind of post as public, means that if I'm cheating, okay, and the only thing I can kind of cheat about what my share is just this one seed, and that really ties the hands of a cheating party. Okay, there's not much that he can do to change this, and in particular, you can set it up so that there's not going to be a way that he can find a different seed here that will instead expand our functions out to some other legal point function. Okay, it's sort of either you can use the honest key that you were given, and that gives us exactly a point function, or if you change your seed here, because everything else is posted and you can't change it, if you change your seed, you're going to end up getting something that's secret sharing of garbage. Okay, so this is closing up all of what I'm going to say about distributed point functions. It's funny, I was a little bit worried I wasn't going to have enough material, but I'm already going a bit too slowly, I see. So let's see what we can squeeze in here. I do want to at least give you some of the insights about how to extend this construction for a different class of functions that instead of point functions are what I'm going to call comparison functions. Okay, so this, you can think about the input space is totally ordered. For example, viewing your bit string as like as a number. And this function is going to evaluate to 1 for everything to the left or less than alpha and 0 otherwise. Okay, and I'm also going to refer to these. So dpf is distributed point function and dcf is distributed comparison function. And let me start with a couple warm-up observations. So first of all, kind of a useful use, I suppose, of DCFs is that if you take 2 of them, you can get arbitrary intervals over, oops, this should not be 0, 1, over something, what I mean over 0, 1, I mean that the output value is either 0 or 1, but the domain is not changing. The domain is 0, 1 to the n. Let me show this by picture. So suppose, for example, I want some interval that has some left and right boundaries that are secret. I can achieve this by taking 2 comparison functions, which are sort of like one-sided intervals, and adding them together. So here, this is why I explicitly put in the over 0, 1, because when you add these together, now these 2 ones are going to, with arithmetic over 0, 1, these will cancel out and give you zeros as you like here. Okay, another quick observation is that actually there's a black box construction that you can get DCF from any DPF if you take n copies. And roughly this is as follows. So so think about this is our target DCF, and think about kind of constructing a tree on top of it. And the idea is that I can express the condition of being less than alpha as exactly an exclusive sum of disjoint conditions, which are each formed as, is this prefix, for example, going to the left right here, okay? Or is the prefix starting with 1 and then 0, 0, and so forth, okay? So this is effectively taking this whole comparison interval and covering it with these subtrees, which are exactly the prefixes that are going off the path to the left from the path alpha. Okay, so how would you do that? For example, I can take the sum of a DPF for this short input, plus a DPF for exactly this prefix, plus a DPF for exactly this prefix, and so forth. Okay, so this is totally black box. It doesn't rely at all on the structure of what the DPF is, but of course this times n is a undesirable overhead. And it turns out that if you open up the box of our specific DPF construction, you can get this with very little additional overhead. And kind of intuitively what's going on here, it's almost leveraging the fact that this DPF construction is this all prefix FSS. So it's unfortunately not identical. It's not exactly the same prefixes as you'd want here. So for example, this all prefix DPF would evaluate to 1 along the path, the prefix is along the path, versus here you want it to evaluate to 1 as soon as you go off the path in the right direction. Okay, so let me give you a sort of an idea of how do you get this cheap overhead, okay? So same picture from the DPF before. You've got, in fact, the same per node invariants are going to be maintained. For every node, you have the secret sharing of some string and some bit. If you're on the path, the bit is different and the strings are different. If you're on the path, they're the same. Okay, this is the same as before. What's new is that I'm going to add in that at each level of a val, I'm going to compute on the side an extra secret shared bit. Okay, so I'm going to denote this by these blue boxes over here. And the goal, okay, is that whenever I'm evaluating my key on some input x, okay, so x is like this periwinkle color here. For example, this x is some potential input you could be evaluating on. That as we evaluate from level to level, I'm also going to generate my bits that are the bits of these secret shared things. And it's going to be the case that the first moment that the input departs from the special path to the left, okay, to the left because I'm interested in less than comparison. So being less than means I need to somehow either be exactly alpha or go to the left from alpha. Okay, so the evaluation on an input X exits this alpha path to the left at some level, exactly if I get secret shares of 1. Okay, or rather kind of we're going to construct it so that I get secret shares of 0, secret shares of 0, and bam, as soon as I know basically now that this input satisfies the predicate. This is precisely the moment when we know that it satisfies that X is less than alpha. At this level, I'm going to somehow generate secret shares of 1. Okay, and then from there, I'm going to continue generating secret shares of 0 again. Okay, so suppose that we could do such a thing. In that case, we're done. Why? Because now I'm going to just kind of modify the final construction where my output will be equal to whatever DPF output I evaluated before. Okay, so that's going to give me, I guess this is like less than or equal to. And if you don't have equal to, you could just get rid of this DPF output. So the final output share is going to be the sum of the bits that we generated, kind of thrown off level by level. And indeed, if my input is less than alpha, that means that exactly one of these is going to be a secret sharing of 1. Otherwise, if my input is greater than or equal to alpha, then all of these will be secret sharing of 0. Okay, so the question remains now, how can we achieve these blue boxes? How can we actually get this extra bit that's thrown off level by level? And for that, let's go back to the magnifying glass, this construction of how to build our correction word delta. Okay, so suppose that I'm here in this familiar situation where we're departing now on the from the special path, where if I go to the left, this is where now I want to get a 1 bit. Okay, so here from the DPF construction, I know that at this node, I have this invariant that the 2 strings are pseudorandom independent and the 2 bits that we're holding are opposite. Okay. So as before, I'll take the string, expand this out, I get some longer pseudorandom strings. Okay, this is so far identical to before. Okay, and now we're adding on this extra thing. So I'm actually going to make a slightly bigger assumption on the PRG. So instead of length doubling, I'm actually going to take lambda bits and spread it out to 2 lambda plus 1, 2, 3, 4 bits. Okay, so this is coming now, like I'm expanding this a little bit more. Okay. And before, so this is copying over what we had before, what our previous delta was, and this was our previous goal. That's not going to change. Okay, the only thing that's going to change is dealing with this kind of new column I'm introducing of these blue boxes. And indeed, what is the goal? Well, as I said, I want this bit to flip to be a secret share of 1 the moment you depart the path to the left. Okay, so here, when I continue on the path, that's not that case. This should be a secret share of 0. But over here, because I'm leaving the path at an exit left, this bit, the goal is that this bit will be a secret share of 1 here. Okay, now, this is a familiar setting. Okay, I have some thing that we're really secret sharing. This is just induced by whatever the PRG expansions garbage give me. Okay, this is the goal of what I want us to be secret sharing. And as before, I can choose these pieces of the correction word to exactly enforce that change. And remember that the correction word, because I'm looking at a point that's on the path, the correction word will be added in because necessarily we have different bits here. Okay, so what is this? This is going to be exactly the bit here to zero it out, and this will be the opposite to give me 1. Okay, so this is one case where this is where we're sitting. Okay, suppose now I'm looking at a different case. Okay, so note what is the difference here? In this case, we just handled was the one where the special path goes to the right and off the path is to the left. Now we actually don't have symmetry because I've got this less than that I want to enforce. So it's actually a slightly different case when the special path goes left, and now the going off the path is going to the right. And think about it. So what's the difference here? So I similarly get some extra strings here. The difference is in the goal. Here, I don't want a 1 on either left or right. Why? Okay, well, the left, I don't want a 1 because I'm continuing on the path. And here to the right, even though I'm exiting the path, I don't want a 1 because I'm leaving the path to the right. That means this input X is too big. It's bigger than alpha. I do not want a 1 in the final outcome. Okay. So in this case, I'll put, in fact, just the same bits here so that we zero these values out. And this is exactly the new construction. So what does this really come down to? Okay, so this first part is copied from the DPF construction. It's identically the DPF construction. Okay, and what I'm adding are these bits along each row. I should observe here, unlike the previous case, my blue bits, these are not actually the same bit value. I'm just keeping them all blue because they all have the same purpose. Okay, but what is this really representing? It's representing, for example, at this level, it would be this bit and this bit. So I don't know what these bits are. It depends on exactly what the computations are. But for example, they're not necessarily the same as each other. Okay, but kind of the important point here is that at every single level, I'm only adding 2 extra bits for each of the keys. Okay, so instead of lambda plus 2 n bits, I have lambda plus 4 n bits. Okay, and this is like, compared to lambda, this doesn't really matter. This is still approximately lambda times n. Okay, I should put one caveat out there. This is the construction if your output group, if your output space is bits, okay? And in fact, what is this blue thing, okay? Suppose that I want my comparison function to actually have a different output group, okay? So instead of a bit, maybe I want this to be a secret sharing of 0 or 1, but over Zn, okay, or over some other general abelian group G, okay? If that's the case, then the same approach works, except that now, oh, keep wanting to click on these things, except that now these values are actually not going to be bits anymore. They're secret sharing bits, but this needs to be an element of the payload space, okay? So if you do have a larger output, then actually the key size does grow somewhat with the output size here. So it's two times the copy of the output group. Okay, but for example, if you are over bits, then this is relatively small. And in fact, as long as your output group has less than security parameter many bits, then this is still a relatively small addition. Okay, and so let me pause ever so briefly and see if there's any questions about the DCF construction before I talk about my final point.
Well, yes and no, because we have questions, but about DPF.
Oh, I see. In that case, let me close everything up, I think, and then maybe I'll take a question right before going to break. Okay, so this is the end of the DCF, of the distributed comparison function construction. And the last thing I want to mention is just a single brief slide about, I mentioned that we have FSS construction for decision trees from one-way function. Okay, so a decision tree, this is some other kind of broader class of functions where you have some topology, okay, where in each node is labeled by some input variable. So for example, this is the first bit of the input, the third bit of the input, and so forth. Okay, and each input bit, each node splits into 2 children corresponding to what is the possible value of that input bit. Okay, and so this describes a model of computation. For example, given an input, I see what is the first bit. If it's 1, I go over here. If the second bit is 0, I go over here, and so forth. And the final leaf label is what you output for a given input. And note that, by the way, this is left as an exercise, that, for example, point functions and comparison functions are special cases of this that are actually in the form of decision lists. So it's like you have one long path and you have just a single output going at each possible value. For point functions, maybe that's more clear. You keep getting 0, 0, 0, 0 as you go off the main path. and comparison functions depends whether you're departing from the left or departing from the right. So I'll leave that for you. Okay. So we have a construction for the class of decision tree programs. It hides some information and it reveals some other information. Okay, so what's hidden are the edge labels, that is which one is 0, which one is 1, and what are the leaf values. Okay, and it reveals the topology and the node labels. Okay, so I thought I had this popping up. So what does this mean? So basically the nodes are public and the structure of the tree is public. That's not being hidden by the key that I'm giving you. But you don't know which way is 0 versus 1, and you don't know what are the final output values. So it's maybe not fully satisfying in the sense that the key size is roughly 4 times the tree size. And unfortunately, also the computation time. If I'm evaluating on a single input, you still have to kind of touch all the nodes of this tree. By the way, this 4 times lambda is appearing here, might look familiar. This construction is roughly a generalization extending our original not optimized construction of DPFs. Unfortunately, the optimizations don't quite work here because it's a slightly more general case. Okay, but there are potential applications here. For example, if you have something like a constant dimension interval. So say, for example, I want to say, is this parameter within this region and also this parameter is in this region? So it's like the and of a few different things. If your dimension gets too high, this gets too complex. But for example, for constant dimension, this is not a problem. Oh, there we go. Now is my animation. This is what's hidden. Okay, so this is closing up part 2. Just to recap, what did you see? Okay, the first was diving into the construction of the most optimized DPF, together with some useful observations of properties. We saw how can you extend this to the more general case of distributed comparison functions. And briefly, I talked a little bit about FSS for decision trees. Okay, so next up is going to be a little bit more free-spirited, a little bit of random applications and extensions of this notion and random cool things about FSS. So I'll see you after the break.
Thank you very much, and we'll meet after the break.